papers in international journals and 5 in national journals are on his credit, and almost 50 papers presented in national and international conferences. He worked on many research projects, more than 7 research projects funded by DST and other organizations. He worked on that. He organized 2 international conferences and 6 workshop short training courses. Many awards are also on his credit. He got a best paper award for the paper presented in international conference on modeling tools for sustainable water resources management held at IIT Hyderabad in December 2014. Best engineering faculty award 2017 presented by National Institute of Technology Warangal and NITW Alumni Association. Thank you, sir. Thank you very much for being with us.
Okay,
Now,
thank you very much. And I request Uma Mahesh sir to please start your session.
Hope my screen is visible to everyone.
Yeah, screen is visible and you are audible.
Yeah, fine. Thank you, mainly Dr. Agarwal and then the other organizing committee members for this FDP. It's always a pleasure to be associated with College of Engineering Aurangabad. I've been a regular visitor to Aurangabad on, say, invitation of Dr. Agarwal. And maybe I always enjoyed his hospitality. Maybe this time I'm missing his hospitality because I'm staying at home and giving the delivery lecture. I would have preferred to come there and then give a lecture, but obviously now it has become a norm that all these courses have become online. It's a different kind of interaction, and then say one advantage that we have here is there are more participants present in this kind of workshops. Anyway, thank you for giving this opportunity to interact with say the participants through my talk. So that the topic on which I'm going to deal with today is simulation modeling. I think over the last few classes, maybe 2 days, last 2 days, you had undergone different lectures on different optimization techniques. So this is not an optimization technique, but what we discuss is how the simulation is useful as an optimization technique in our say applications. So this is an overview of my talk. I'll just start my introduction with a very brief review of the concepts of modeling, because what we are talking about in all these topics that you're dealing with in this course is modeling. Maybe there could be an overlap with what others would have discussed already, but I feel it's necessary for you to understand the important significance of modeling. And then I'll be talking about, say, the various concept system analysis, and with reference to systems analysis, how this optimization techniques and say the problems associated with the optimization techniques, and where simulation comes into picture here. And then I'll focus on the simulation. I'll just discuss about types of simulation, need for simulation models, and we'll talk about both event-based and continuous simulation, and maybe so I'll be giving an example of event-based simulations, and then another example of Monte Carlo simulation, and then maybe I'll demonstrate the application of simulation through just a few examples that I've taken up, small examples, which will demonstrate the usefulness of simulation, because in this maybe talk, 2 hours talk, I will not be able to give a real example, but I'll just try to give it some simple examples to which I think you'll be able to appreciate the importance or significance of simulation. You have to pardon me, I think the participants are coming from across different branches, but my specialization is water resources, and I've been using these techniques in water resources. So obviously I tend to give more examples of water resource engineering they read to some extent civil engineering. So other branches, I think they should be able to correlate what I'm giving examples with their own specializations. Okay, there are a lot of logic. In fact, the applications part, I think, is similar, whichever branch of engineering you are. The techniques, the way we use the techniques is more important than, say, I mean, that's not, I think, the purpose of this kind of lectures. So, I think you all understand the importance of modeling. And in fact, the entire course is based on what you're going to talk about in as modeling. Okay. Now, I just borrowed to, in fact, explain the need for, say, the significance of modeling in engineering applications. I borrowed a quotation from Ruth and Weiner. I'm not sure where this quotation was from which book I've taken this. No substantial part of the universe is so simple that it can be grasped and controlled without abstraction. So we're dealing with large number of complex systems, and when you deal with these complex systems, it's very difficult for us to actually grasp the entire system. So always we try to go for a simplified version of that complex system. That's where what we call as abstraction. So a model is something similar to an abstract. So what's an abstract? Abstract actually hides the details and gives you only the gist of what is required or what is there in that. For example, you're talking about an abstract of a paper, an abstract of a thesis. You just give only the gist, adding the details. So abstraction, so a model is something similar to this. You're only trying to extract what is important for you and then try to put them in your model and then hide more complex details. So the reason why I can say it's a kind of an abstraction process. So abstraction consists of replacing the parts of the universe under consideration, a model of similar but simpler structure. And the most important is models to be formal or intellectual or material, whatever it is, are a central necessity of scientific research. So any scientific analysis, any scientific study that we deal with, whether engineering or science, I think models have become important tools for which we understand and try to study the problems. So maybe those who have been dealing with models, you look at, if you look at the picture, you try to look at the books on dealing with modeling, you find different types of models. And broadly, they can classify into 4 categories, what we use in engineering, most of the engineering branches. Like, for example, mathematical models. So the entire course talks about mathematical modeling here. Or maybe, especially civil engineers and mechanical engineers are very familiar with the physical models because we do a lot of experimental work in laboratories using physical models, where we go and construct a physical model. For example, I think we in a laboratory, we try to explain to students how a centrifugal pump works, how a turbine works. So we have a small scale version of that machine, and then the students work on it and then try to understand the behavior of that machine. So this is a kind of physical model. Or maybe civil engineers go to a material testing lab and try to understand how a simply support beam behaves or how a cantilever beam behaves, and try to understand through a small simple models there. So they are called physical models, and we have what we call as conceptual models, which are typically mathematical models. So the difference here is the way the mathematics is constructed is based on a concept, not based on the actual physical reality. And then analog models where we try to use some analogy, especially in water sources. About 30, 40 years back, there was a lot of studies on analog models where people used to try to use analogy between the flow of electricity and flow of water, and then try to understand the flow of water through the analogical models using electrical flows. Maybe flow through porous media like seepage to a thin dam. This kind of studies were made using this analog models. But among all these things, now these days, mathematical models have become more popular. The reason is we have, say, in fact, when compared to about 20 or 30 years back, we have very good computation facilities. So we have the computers on our desk and then on our lab, and then we'll be able to work with these mathematical models. So we have good computation facilities because mathematical models need a lot of computation. So that's how the mathematical models have become very more popular, and many of us try to use these mathematical models to understand the complex system that we deal with. So these mathematical models have been used in engineering, like for example, simulation. That's what I'm going to talk about today. Or the simulation maybe could be used for analyzing the behavior of a system, or like say, for example, I'm interested in knowing what is the erosion process taking place in a watershed. So maybe I can use a simulation model, develop a hydrology model which simulates the process of erosion, and then maybe I can try to understand how the erosion process takes place, or better understanding system, or designing new processes, or the design of controllers. So I think the last two are what the main topic of this course here, because this course you're trying to learn the various automation techniques, which basically are useful in design of a process, design of a policy, design of a system, or design of control systems for the different process. So these mathematical models can further be classified into different categories. Maybe we can call them as descriptive models or prescriptive models. This classification is significant again from the point of view of this topic of this course FDP that we are dealing with here. Descriptive models are actually models which help us to understand or describe a behavior of a system. Okay. For example, in structural beam, you learn about the deformation of a beam. Say, simply support beam will subjected to load. We use the laws of mechanics, of the principles of mechanics, and derive an expression for the deformation or the movements produced or stresses produced in the beam. So this I can call as a descriptive model. Or for example, a head loss in a pipe. I have an expression for head loss in a pipe. So the head loss in a pipe again is a model. Again, you derive from laws of physics, and this model describes the behavior of the say pipe system. Whereas what we are talking about in this course is what we call as prescriptive models. As you know, a prescription is needed when you have a problem. So when you have a problem, you have go to a doctor gives a prescription. So here prescriptive models are the models which help us to solve a problem, and they help us in decision making. So all these optimization techniques and the way we are going to talk about simulation in today's lecture, all this I can classify under the category of prescriptive model, because we are trying to use these models for say prescribing a solution or trying to make a decision. So they are all the models which are used for decision. But please note that this classification is like only for understanding, but it's very subtle. The sense that without the knowledge of descriptive models, I think descriptive models do not exist. Because unless you say, for example, a doctor has to understand how, say, for example, a cardiologist has to understand how a heart say behaves, then only the cardiologist will be able to diagnose say problems a patient has and then prescribe some treatment for it. The same way, any problem that you are trying to solve, unless you understand the behavioral system, which is given only by descriptive models, is very say we cannot prescribe a solution. So why they actually go in hand. Descriptive models actually try to make use of are built upon the descriptive models. As a classification, again, why I listed this here, because again in simulation, in fact, as you will see later, we'll be more discussing about stochastic models, because the simulation is more useful, especially dealing with very complex stochastic systems. So in a system, if there are no uncertainties and you assume that every input or parameters are known to you, then we deem such a system as a deterministic system. But unfortunately, in real life, it's not like there are a lot of uncertainties that we have to deal with. So when we try to incorporate the uncertainties into a model, then this becomes a stochastic model. So we are dealing with what we call as mathematical models of decision making, which help us in a rational approach for decision making. Based on what we call problem solving. It's called in different names: operation research, decision science, systems analysis. So there's a different names with which it's called. Maybe systems analysis is a broader term, because systems analysis doesn't mean that only mathematical models. It is a process through which you analyze a problem and then try to develop a solution to the problem. But in the process, when we're dealing with complex systems, we use mathematical models, and these mathematical models are called optimization techniques, operational techniques, and so on. And most of these techniques, I think, other people also would have discussed this. Most of these techniques have evolved during the Second World War. There was a lot of crunch for resources, manpower, other resources, and all those things. And so, this most of these techniques that we use today for automation, they work. So initially, there's a developed in the and then slowly it can say enter into the industry management, and then into every discipline of engineering. So system analysis is maybe just a very brief introduction to the concept of system analysis, because that's important for me to define the way the simulation is useful here. So it's a kind of analytical study where the decision maker is trying to identify and select a preferred course of action from all different alternatives. That's where you are trying to use, whether you use linear programming or dynamic programming or any other automation technique. What is that you are trying to do here? You have a set of alternatives, a large list of alternatives. You are trying to pick up what is the best alternative. You're trying to find out the best alternative. So this system analysis is a process in which we are trying to understand the problem and then develop analytical process through which you understand the problem and develop a solution. So it's a problem solving technique where you are trying to make a replica of the real world problem in terms of some model, like once you construct model, whether you use linear programming or dynamic programming or some other automation technique, depends upon the structure of your model. And then you are trying to play with that model and try to understand the behavior and thus understand or find out what's the best course of action that you take for a given situation. So again, this not spend much time. I think system is something which we use very frequently, and then there are a lot of definition of system. I can simply say it's a collection of parts of which interact with each other, and then to say specific purpose. Like for example, a cooling system in a car may have number of components like radiator, fan, water pump, thermostat, board systems. They themselves individually systems, but they're all assembled together to serve a particular purpose. That is to cool the car, say to develop a cooling system in the car. So that's how a set of objects which interact in regular different manner is what we call a system. And you find different, say, definition of system. But maybe in a simple format, I can put a system in a schematic way like this, where you have a system, I just prepared the form of box like this, which receives some inputs and then applies some kind of transformation to produce outputs. So the transformation could be a function of the parameters to describe the behavior of the system, the characteristic of the system, and then maybe the policies which govern the say input of the system. And thus, when you apply this transformation function omega onto the input, you get an input. Okay, so this is a typical representation of the system. And with reference to this representation, okay, maybe we can talk about a characteristic. So they have a structure and organization, and then there exists some function relation between the different components to understand what the function relation is, and what is the relation between the input output. And obviously, system is not isolated; it's a part of a larger system, which is the environment. And I can give a number of examples for this. Say, for example, I'm just talking about irrigation system. So irrigation system, for example, you are diverting water. There's water at some point. You are diverting the water maybe through a storage or a diversion system. And then you have different components like canals, regulators, structures, gates, etc. And then certain policies which govern the way you are operating or locating the water or distributing the water, and then so the interaction that takes place between the officials operating the reservoir systems and then the farmers who are trying to use the water. So of all these interactions, what's happening is the water that you're getting from the source is finally transformed onto the field where that is required for agriculture. So you can see that the components could be classified into different parts, like you have structural components like canals, regulators, structures, gates, etc. So maybe you have to do design of this the components. And similarly, you also need a kind of a policy which will help us to operate or say allocate the water from through the system. Okay, so this also maybe is a component. If I use a computer terminology, I may call this a hardware, this a software. But see, all these components need to be designed when you are developing a system like this. So when I say design, so it's not design doesn't mean that you are trying to design a structure or a structure element, but it could be a policy, it could be a scheme, or it could be a procedure. Now, with reference to this concept of system, now I would like to define the different types of problems that we have. So in a system, if I take a different system, we have inputs, parameters, and outputs. The parameters describe the behavior of the system, and you have outputs, inputs. Now, in a particular problem, uh, any two of them are known, and the third one you are trying to find out. So based on that, all the problems that we come across in engineering can be classified into three different categories. One first category is where you know the input, you know the system characteristics in terms of parameters of behavior and all those things. And what you're trying to find out is what is the say output. Say I have a simply support beam, there's a load coming on the simply support beam. So what's the deformation? What are the stresses? This is a direct problem. Or let's say, I have maybe I'll take a catchment, like there's rainfall occurring on a, say, for example, a area. And so what's the amount produced per day? So the catchment characteristic are known. So you are trying to find out what the amount coming from the day. Say that rainfall event. So this kind of problems are what we call as direct problems, where you already know the system characteristic and be able to improve. And in fact, what a simulation does is this. If you know the input for a given input, how the system behaves and what is the output produced system is what actually we are trying to do through simulation. So maybe I also call this category of problems as simulation. Whereas the other category, other side we have problems where you know the input and you know the output, you are trying to find out what is the system which is actually causing this transformation. If you are trying to understand how a system is behaving for an existing system, it becomes an inverse problem. Like for example, I know that y is linear related to x. Let's say y and x are two linear. So you are trying to develop an equation y is equal to x plus b. The relation between y and x as y is equal to x plus b. So you are trying to find a and p. So this a and p actually explain the relation between the input x and the output y. So I can say the parameters. So this parameter estimation problems become what you call as inverse problems. They're called inverse problems. So you have observed the output, you have known the input for a given input, and then you are trying to find the parameters. But what we are talking about now, I'm more interested here to explain here, is design problems, where for a given input, you'd like to design a system which will give you a desired kind of output, certain type of required output. So this is what you could design. So you're designing any design problem. Say this is what you're trying to do. For example, you're designing, maybe many of your faculty members are different, institutes, and maybe one of the tasks that you always do is to design the curriculum for your for example, undergraduate program, BTech. So when you design the curriculum, what is that you are doing here? You know what kind of students you're going to get to your program. You know the qualification. So that's the input. And based on the requirements of the market, you have actually, okay, these are the qualifications required. By the time the student completes the 4 years and goes out as a BTech in civil engineering or BTech in electronics engineering or BTech in computer science. So what is to be done here in between so that this transformation takes place? So that's what you are trying to design. So this is called a design problem. A design. So it's a design of a scheme or design of an equipment, a design of a machine. So all this come under this category of design problems. Okay. Now, so in fact, all the optimization techniques that you're learning or you're learning in this course, they're all meant for this kind of problems. You are trying to solve this kind of problems, particular design problems, where you're trying to design a system which will give you the required kind of output. Now, the question is how the simulation comes into the picture again. That's what I'm going to talk about as part of my lecture. Then I'll try to explain how simulation is useful as a design problem. Though actually simulation doesn't come under this category of problem, but it is actually a kind of a directive. There's a third category problem, what you call as detection problem, instrument problem, where you know the system characteristics, you know what is the output, and you are trying to find out what has caused this. Okay, this kind of problems, okay, I think DC electronics people, they know because signal processing, I think they do this kind of this thing. And maybe structure engineers, for example, they want to find out a structure has failed and they try to find out what causes that, what caused the failure of the structure. They try to do that reverse analysis, and then this all this kind of problems are called detection problems. So though this entire course where you are learning the optimization techniques, the focus of the optimization techniques is design problems, where you are trying to design something which I try to explain. I just gave some examples for this. I think I have been giving this example, but say if you look at the representation of system like this, now what you are trying to hear is okay, you have different inputs. The inputs can be classified as controlled, partially controlled, uncontrolled, depending upon to what extent you have control on the inputs. And then the outputs could be desirable, undesirable, or neutral. Undesirable are the negative impacts. I'll say all the costs are undesirable. Cost, when I say any negative consequence of activity take up is obviously a kind of cost. So now what is that you are trying to do? You want to design a system which will maximize the desirable outputs and minimize the undesirable outputs through by control or partially controlled by manipulating the controlled or partially controlled, say, variables. So any problem that you have been discussing in the last few days, you try to put into this picture and try to look at that from this perspective. So what you are trying to do here is you are trying to find out a system which will maximize something, so maximize desirable outputs or minimize the undesirable outputs. Through what? You have a set of decision variables, what you call it a decision variables, to which you are controlling these values of decision variables or manipulating this decision variables so that you will achieve the desired, say, objective. Okay. Now, here comes, okay, I talked about optimizations. Optimization basically where you are trying to use, say, more mathematical models for, as I said just now, to design a system which will maximize the desirable outputs and minimize the undesirable outputs, like through the through your control of the say these things, control of desirable and undesirable outputs. Okay. Now we are talking about simulation as a part of optimization. So there's a difference between simulation and optimization. An optimization model, what you're doing is, okay, I just borrowed this picture from a book by Water Systems Planning and Management. And as I mentioned earlier, obviously my examples that I give are water system. So what is mentioned here, water system, but I can easily replace this water system by any other system. You have some inputs, and what you're doing is you're trying to design a system and develop an operating policy. Okay, so that's what optimization model tries to do. You want certain outputs. So based on that, you design a system and develop an operating policy. So this answers the question like, what is to be done? If I want this kind of outputs for given these inputs, what has to be done? So I'm trying to answer a question, what is to be done by an optimization? But whereas a simulation model, so okay, you have identified a design or an operating policy. So, and you would like to know what happens if I use this design. So, see, look at the type of question that optimization model and simulation model are trying to answer. An optimization model is trying to answer what is to be done on a given for achieving this. Whereas a simulation model is trying to answer the question, what happens if I do this? What kind of outputs will I get if I do this? No, there's not a difference between these two. Now, as you will see now, in fact, maybe simulation model directly is not an optimization model, but actually it will help us to maybe improve the usage of optimization, because optimization model has their limitations. And so this simulation models help us to overcome certain difficulties of this. And the reason why most of the time we try to make use of both of them simultaneously. It's not that say we replace simulation models with optimization models, or optimization models are always use only optimization models. So we try to use them iteratively so that we can improve. So you have an optimization model which can actually reduce say alternatives, and then for different alternatives you can try to evaluate the performance using simulation, and then use this iteratively in order to improve your say the system design. So with this background of modeling and system analysis and all those things, let's move into the topic of today's discussion, the simulation. So what is simulation? Sorry. discussing about simulation, but let me formally define a simulation. Uh, Maybe I can say it's an act of imitating the behavior of some situation, some process by means of something suitably unlocked. I'm not saying mathematical only through math. A kind of process, if you are trying to imitate the behavior of something. Okay. Say maybe, for example, what a mimicry artist does is a kind of simulation. He or she will try to imitate the behavior of maybe different animals or different human beings in different situations. So that's a kind of imitation. Or maybe I will use some kind of analogy to imitate the behavior of a certain characteristics of a system. Like I was talking about analogy of electric flow and fluid flow. So I know that these two are similar. So I may use to simulate the flow of a fluid by using a simple electrical system, which will represent the say this fluid flow system, and then imitate it. Okay, and maybe there are a lot of say simulation systems which will try to simulate, for example, uh, pilot training. They're what we call as flight simulators. The flight simulators are say a very say is a kind of maybe a process for which the pilots are trained on the say maybe on say controlling an aircraft without actually experiencing flying on a flight. So before, because obviously pilot training is a very costly affair, so they have flight simulators where so it's a kind of process where we're trying to simulate. In fact, I think I understand. In fact, I've seen one or two places today. If I did car driving, also car driving simulators also come. So you try to imitate the way you drive a car, and then you try to understand the control of different say parts of the car through a simulator, and then actually go to the real system. And I think many of us are familiar with the lot of games which simulate different activities, like, for example, car racing, motorcycle racing, or war games. They're all simulation games which try to imitate certain real life situations. And then we feel like we are participating in that actual system. So, but what we are talking about here is a simulation through a mathematical model, where you try to consider a model and then use that for simulating the real system. So simulation in general is to pretend that you are dealing with a real system actually while you are working with imitation. Like I said, say maybe a pilot tries to undergo a training in the beginning in a flight simulator. So the environment is created such a way that the pilot feels that he's actually sitting in an aircraft and then running an aircraft, real aircraft, before actually the pilot enters into a real aircraft. So we are talking about simulation models, a mathematical model for simulation, what we use. So I just gave a very broad classification of this simulation models, how they are classified in different categories. When I say simulation model could be deterministic or stochastic. I think this classification I already discussed. If you are dealing with uncertainty, if you assume that everything is deterministic, if there is no uncertainty at all, then we talk about what you call deterministic models. Whereas when you're dealing with uncertainty, or you're trying to incorporate uncertainty that occurs in our real life into the models, then we have what we call as a stochastic simulation. Okay. Both have their own advantages. Both are being used. For example, if you are trying to say simulate, say in such situations we neglect the say for example the uncertainties. Like for example, you would want to simulate a hydraulic structure, say any hydraulic structure. For example, a dam has been designed. Most of hydraulic structures actually they are say studied in a physical laboratory with a physical model before actually they're constructed. So what we are trying to do is a simulation model. Maybe though it's not a mathematical model, what we're trying to do here is assuming no uncertainty, but we are trying to construct model and see how it behaves. Like a replica of the model in a laboratory and then understand its behavior. Or let's say, for example, you're trying to understand the behavior of a structure that you're trying to design. So maybe you don't deal with the uncertainty there. You assume that all the loads are known, all the loads coming in the system are known, and then say, analyze the structure, simulate the structure, and understand behavior. So it's obviously a deterministic. Again, we can classify deterministic or stochastic models into two categories: static or dynamic. This depends upon the time range. Is the system, say, uh, time invariant or time variant? What I mean by time invariant is its behavior or its, the system doesn't, its characteristic do not change with time. It's then we say it's a static. Whereas a dynamic system is where it undergoes continuous changes. So depending upon this, you may classify your models as static or dynamic. One of the static, in fact, as part of my course, I'll be talking about stochastic models only. And one example that we're taking is a static stochastic model, which usually is done through what we call as multi-corridor simulation. That's what I'm going to introduce later as part of my multi-corridor simulation. Now, a dynamic model could be again, this dynamic model is where the static is, for example, I have, say, I'll take an example of a structure. For example, I have a simply support beam and applying a load, and the load is fixed. Then I know how it behaves. So this is a static. But a dynamic system is where, say, for example, if I take the same structure, say how it behaves when it says undergoing a say cyclic load. For example, there is a earthquake. So obviously, the type of analysis that we do is the dynamic analysis, because with time the loading is changing because of the, maybe even if it's occurring for a short time, with a short time of the during that quake, the loading on the structure is changing because of the say seismic induced acceleration, and that obviously the way we analyze that is simulation. So when I deal with dynamic could be again discrete or continuous, again depending upon how you are taking the time step. Is it, are you taking a discrete time step or a continuous time step? You're taking discrete time step. If the time is discrete, then it's called discrete simulation or continuous. Again, most of the time for the convenience of mathematics, we always, even in a continuous system, example, if I take a catchment, I'm trying to model a catchment, simulate a catchment for a rainfall event. Rainfall is a continuous, say, event, and then obviously the say the analysis should be dynamic and continuous over time. But the measurements and other inputs that I'm giving, I'll not be able to measure rainfall continuously with time. I may use some discrete interval, like for example 1 hour or 1 day, and then give the inputs in terms of discrete time steps. So obviously, though the system is continuous and dynamic, they are not actually simulating as continuously with types prime, but they are using you're simulating with a discrete time. So most of the time, it's convenient for us to mathematically go for discrete time step only. And so that's the other thing that I am going to talk about as part of this, for example, discrete event simulation. So for one particular event, how that you simulate the system. So maybe continuing with the types of simulation, as said, say discrete event-based simulation. So example, I'm just talking about only things which I'm going to be here. You have a catchment. Okay, like for example, you have taken urban area. Okay, I think this everyone can understand, even though you are not a water engineer. You take an urban area, a city, a town, and maybe you are interested to know what happens when a severe rainfall occurs on that. Because these days you find most of the urban areas are getting affected. Flooding has become a major concern in most of the cities and towns in India because of various reasons. And so maybe as an engineer, I would like to know what happens when a storm event happens. So which areas get inundated, or which areas are problematic, or where there could be, say, maybe overflow of the drains. So this is, say, I would like to know how the catchment is going to respond to a storm. So this becomes what you call as discrete event based. Means here you're trying to simulate a system, and for a particular single event only, you are trying to simulate this for a single storm. Okay. But sometimes a single, say, discrete event is here I'm talking, and here is not The discrete is not with respect to time step. I'm talking about discrete, say, concept of discrete and continuous with respect to an event. With respect to, so here I'm talking about a single event. This is why I said discrete event. I may simulate this for, say, for example, I could have identified some severe storms that have occurred over the past few years or the past data, and then try to simulate the, say, the city, the behavior of the urban drainage system for these events. So each event is different, discrete, and so it's called, that's the reason why I call this discrete events. So this is useful for us to understand how a catchment responds when a particular event, storm event occurs, and then maybe based on that, what kind of say measures you need to take up so that for a rainfall occurs, when the rainfall is forecasted. So this is where a discrete event based simulation will be useful. Whereas in hydrology, same hydrology, I may use a continuous simulation where here again, I'm not, when I say continuous, I'm not again referring to time here. I'm talking about, so I would like to know how the urban drainage system, say in the city, you have an urban drainage system, how it is going to behave over the entire monsoon season. It's not a single event. Now, say if you consider, for example, as rainfall has occurred and then within 2 days another rainfall event has occurred. So obviously there's a dependence between these two. I cannot isolate these two events. So then in that case, I would like to know how over a continuous span of time, this system is going to behave. So I'm not identifying single event. I have multiple events here sequentially occurring. So I'm talking about a sequential occurrence of all these events. And that's how, say, maybe talk about that what we call as continuous. Okay. For a long, again, so this is an example of discrete in terms of events, so discrete or continuous. And as far as stochastic simulation is concerned, as it we talked about, say maybe the discrete time, I use discrete time step, we use what we call as multi-problem simulation. This can be used for example, your queuing system. I think many of you know what's a queuing system. I'll just give an example of queuing system. For example, you're designing a toll gate system on a highway. Okay. And so when I say design, what is it you're looking at? How many, say, gates should be there? How many connecting points should be there? That all this design depends upon the traffic. But your traffic is uncertain. The traffic flow is uncertain. You have variations. So maybe you design for an average condition, but like to know how the system is going to behave for different conditions. So maybe you can take a worst event or a worst case event, like for example, on a particular day, because of some reason, there's a heavy traffic flow on that day. How does your, say, queuing system, here the queuing system is the target system. How does it behave? What is the waiting time? How much time the cars have to wait and what will be the accumulation? All these things are understood. Or maybe I would like to know the behavior over a long span of time. For example, over an entire 1 year, I'll try to simulate it with, say, under uncertain traffic and then see on average how it behaves, what are the characteristics of the queuing system, behavior of the queuing system. So I'll just give an example of traffic control system, the toll gate system. It could be a signal system and a traffic intersection in a city, or it could be any other queuing system that maybe a doctor queuing system that you maybe you have used in your own specializations. Or maybe to simulate an inventory control system. So you have, especially like in inventory control is, say, with, for example, in the construction industry, you maintain, and what is the inventory? You are making orders and then you are storing the items. So to store your items, you need to spend some money, and because you need to have a storage system there, and you're trying to spend something. At the same time, say if you have a large stock that you are honestly wasting a lot of space and then a lot of money for that. As we have small stock, there's a possibility that you have shortages because suddenly when there is demand, you don't find it. And the problem with this kind of systems is demand could be uncertain. So when you have a uncertain demand system, the design that you make, whatever inventory system that you design, how good is this design and how it behaves, this is something which you would like to simulate. Maybe I'll be taking an example and make example for this part of my. Okay. Or an example I take from water sources, simulating the operation of reservoir. So I have a reservoir system which is built, and then the reservoir is meant for different activities. You want to meet water say, use the water for various activities like irrigation, water supply, hydropower generation. Maybe the reservoir could be used even for flood control. So there are different types of. I think there are some questions that has come, but can I answer the questions later, or should I answer now? Because reading the messages is difficult for me while going to lecture. Okay, I think it's better that I answer all the questions that are coming up, because I just see a message, someone has put a question. So I'll try to answer that at the end of my lecture. Okay, please bear with me. Maybe it would have been say, a physical lecture, I would have answered on time, but here I think seeing that and answering that would be difficult for me. Okay, so you have a reservoir system and then you are trying to operate a reservoir. So operate is how, say, as flows come into the reservoir, how much water is released, how to allocate water for my different activities, and then other things. So again, the problem here is the flows that are coming to the reservoir are uncertain. In inventory system, in reservoir operation system, are similar actually in a way. Only difference here is maybe inventory demand is uncertain. The reservoir inflows are more uncertain. Okay, demand also could be uncertain, but most of the time we assume the demand is known to us, and only the inflows are uncertain. Whereas inventory control system, the inputs are in our control, so they are known, definitely, but your demands are uncertain. So both come under different category. I'll be explaining, maybe I'll take an example of operational reservoir, also as an example here as part of this lecture, where I will show you, say, maybe in terms of what we call as event-based simulation. So this simulation says that we use applied in different, say, there are different applications of the simulation. Design operation of inventory control system, I just mentioned, design operation of fuel systems, resource allocation, traffic control, design and operation reservoirs, operational distribution systems. It could be a water distribution system, or maybe, for example, a distribution system, electrical distribution system, or so it could be any distribution system. So there are different applications that you come across with simulation. Okay. So how do we build a simulation? This, like, I think you have learned how to build a movie when you look at linear programming or array programming or other automation techniques. You have learned how a structure of the model, say, that's why simulation models are nice. And I think one of the advantages that simulation models have is there's no specific structure for simulation. For example, I have to use linear programming. The mathematical model that I'm going to construct would need to have a structure. The objective function constraints also the they must be of some specific. That's one of the limitations of optimization model. When you try to develop an optimization model for a particular problem, you are bound by the structure. So because the structure defines what method you're going to use, and because of limitations that you have in terms of the mathematical models, maybe you are constrained to, for example, convert your problem into linear programming problem, or convert it, make certain assumptions so that it is of some simpler structure which can be solved more easily. But that kind of constraint is not there as far as simulation model is concerned. There's no kind of defined indefinite mathematical structure. It could be a fairy type of structure. It could be made up of differential equations, could be made of integral equations, or could be of any type of format that you can have, linear or non-linear, whatever it is. But when you try to develop a simulation model, build a simulation model, first you try to define what is the state of the system. Okay. For example, I'm talking about a reservoir. Or define a state of system. A state of system could be what is the amount of water stored in the reservoir at this moment. Okay. Or let's say I'm talking about inventory control system. So maybe the state of system would be what is the stock that I have in my inventory at the moment. Or let's say I'm talking about a queuing system. So maybe the state of system could be what's the length of queue now? How many customers are there in the queue now at this moment? At that point of time that you open. Okay, so this is say you need to understand how you when in the problem that you are taking up, you need to first define what is meant by the state of the system. How do you find the state of the system? And then identify what will be the different possible states, possible values that this system states can take. Example again, if I take a reservoir, the reservoir could be empty when the reservoir storage is zero, and the maximum storage is fixed because there is a capacity and you cannot exceed the capacity. So your storage can take any value between zero to that capacity reservoir. So you can find out what are the possible states of the system. The same way, for every problem, you can try to identify what are the possible states, what would be the values that the state of system can take. And now try to define what is an event. An event which causes change in the state of system. For example, reservoir, if I consider the reservoir, there is an inflow and then demand. An inventory system, there is a demand for something. So there is maybe or you're placing an order, and so you have got an order, and then you have stock in the reservoir. And an event occurs when there is you are trying to take out something from the stock for meeting some limit. Or in the reservoir, you are trying to take out some water from the reservoir to meet it. Or in the case of your queuing system, you have served the customer. You finish the task that the customer has to do. For example, in a toll gate system, okay, you collect the toll and then the car or the vehicle is released from the toll gate. So this causes a change in the system. That means an event is something which will happen and will cause a change in the state of system. Okay, so and this change usually we are dealing with changes the state over time. That means with time. So there's a time step. For example, a reservoir operation. I may consider a week or month as my time step. So I'll be operating the reservoir once in a month. So I'll decide how much water is in the reservoir once in a month, or once in a week, or once in fortnight. So that time step is important. So the time step, how you simulate the time step means you need to have a kind of clock in your simulation model. It's not when I say it's clock, it's a kind of again a simulation system. So you are trying to define the time step. How you say, okay, this time is over and you're going to next. So that's how you need to simulate the time step and do it what you call a simulation. And then especially when you are dealing with the strata systems, the possible events could be scenarios and events could be different. So you have to develop say situations, what are the possible scenarios that can happen? What are the possible events that can happen? And because you would like to know what happens in the different conditions. So you need to have a method through which you will be able to generate the different possible scenarios and the events of various kinds. I just gave an example earlier for sample driven systems. So one way of generating the possible scenarios, I just use the past data. I say maybe have rainfall records for past years. I identify maybe certain major rainfall events out of this total data they have, and then take them as the possible scenarios, and then simulate the upper drainage system that I have designed for under these scenarios and see how the system is behaving. Okay. Or let's say, for example, you are trying to simulate a traffic control system, the toll gate system. So you try to find out the past data of the traffic at that location and identify certain events which could be critical to your system. So and then try to say this. Or maybe you can synthetically generate for scenarios, so visualize different types of situations. This can happen, this what can do for this. We need to have some kind of methodology and mechanism through which you will be able to generate the possible scenarios or events. And then so how the transition takes place. So basically your model should be able to identify how the transition from one state to another state happens. So a state transition formula which is based on the behavior of system or the physical system that you are dealing with, the chemical system. So these are the steps involved in building a simulation model and how it model. Maybe it's better I explain them all these things through certain small case studies. Again, I'm not able to take large case studies here, but maybe small problems. Again, it's maybe in a class say a system like this, a class online system like this, it's difficult for me to actually solve the problem here, unlike in a physical classroom where I can take out a chart piece and then write on the board and solve that. So I'll just try simple examples and show how you can solve these problems and how this will help you to understand how the simulation models can be built and how they can be used for. So I'll take an example which is like a specialization of mine that started working on this reservoir systems. I think like Dr. Regalwar, who also I think has done a lot of work on optimal operational reservoir and simulation of reservoirs and all those things. So I'll just take a simple example of a single reservoir. I borrowed this problem from a, I just quote the problem very in a simple way. Have a reservoir and what refers to reservoir in the form of a triangle, like this is a river, and across the river you have constructed a dam and then you have constructed a reservoir. Let's say the K represents a capacitor reservoir. Okay. And T here is a subscript that I'm using to represent time step, time. Okay. So obviously, though it's a continuous process because in a reservoir, the flows will be coming continuously and then you will be releasing water continuously. We don't deal over a continuous time, but we'll take a discrete time step, usually a week, a fortnight, or maybe a month. So time here T is a time at which I'm talking about. So maybe if I take, for example, if I say month, okay. So ST here represents the storage at the beginning of that month. Maybe some of these terminology could have been introduced in other lectures where you would have talked about reservoir operation problems. Okay. QT is the flow coming into the reservoir in that time. And RT is the amount of water that is releasing to the reservoir in that time. T. And let's say there are three activities. For example, I may say irrigation, hydropower generation, and maybe some other like water supply, electricity. So these are the amount of water that you are allocating for different activities. The first activity you are putting X1, second activity X2, third activity X3, and so this is the amount of water. So when I take an operating policy, when I say an operating policy of reservoir, I need to have a policy which will decide how much water has to be released and how that water is allocated among the various activities. There are two things. One is how much water is to be released in the reservoir and how this water is allocated among the activities. Now, the problem here is that its inflow is uncertain. So depending upon the inflow and this ST together decide how much water is out of the reservoir. Because ST is already existing in the reservoir at the beginning of that time step, and QT is what is coming to the reservoir. So this is the total amount of water you have it. And from this, you decide how much water is to release from the reservoir. And if the amount of water you're releasing most of the time cannot be meeting the total requirements of all three activities put together, because most of the time there could be deficit. So there's a deficit when you are not, say, each of them have some demand, but not able to meet it for total demand. Then how do we allocate the water among the three activities? So this, you need to have a policy for this. Okay. So you need to have a reservoir operation policy and a water allocation policy. So we need to define these two policies. I define these two policies in a very, very simple elementary way. Okay. This is called what is known as a standard operating policy. Those who are water source in this, I think they know what it means by this. So now if the amount of water that is available, ST plus QT, is less than what is your minimum target, minimum requirement. Say I call this as least target, then you release whatever is available. Okay, that's how this line goes like this. Once your QT plus ST is more than the amount minimum release, then you release as per this. But beyond certain point, what happens is your reservoir becomes full. Then you release excess water than what is required because you cannot keep that water in the reservoir because you'll not be able to store that water. You start releasing more. In fact, I can put it mathematically in a simple way like this. If your ST plus QT is less than the minimum requirement, then the release will be equal to ST plus QT itself. Otherwise, if RT, say ST plus QT is between the minimum requirement plus K in between these two values, release only this much. And if it is more, then your release is ST plus QT minus K. You just store what is the full, so make the reservoir full, and what is excess, release it. So that's how this line comes, this red line. Okay. So this is a typical policy, but I can modify the policy. For example, I may release less water than what I have to say. I'm saying that all water release, but you want to keep it for a drought period. So then in the case you release less water. So maybe you may change this here. So maybe instead of this line, following this line, you may change, modify a line like this and then modify this. It's what we call as edging, and then you may modify this, and you can have any number of operating policies defined based on this. That's the concept. You can slightly modify and create number of operating policies. Okay. The question is, which is best? Okay. In fact, I think you would have, I don't know what example was taken and stochastic programming model that was discussed with the model by the person. But you would have taken an example of reservoir operation also. So maybe we can use stochastic programming model to develop an operating policy. Okay, what I'm going to talk about here is how that operating policy, based on that operating policy, we would like to know how the system is going to be. Okay, so similarly, I may have some kind of allocation policy, like how much water. So, for example, some minimum release has to be done in the river. So, some water has to be always in the river. So, the blue line represents how much you are releasing into the river downstream, and the different lines like user 1 is yellow line, this line is user 2, this is user 3. So this maybe you define some policy based on some means. I'm not going to details here. Maybe here also you may have some kind of say an optimization model. Like for example, I may use an earning power model here also to define this policy, auto allocation policy based on the maximization of benefits I get from this allocation model allocation. Okay. So in fact, I have borrowed this problem from a book. I said water systems planning and management, models and applications. It's a book published by UNESCO. So this is a typical problem. So if I know this is both an optimization problem and a simulation. Maybe through an optimization model, I may develop an optimal operating policy rather than what I am doing. I'm just using here a simple, no optimization here. I just use some kind of a standard operating policy. But I can modify this by using some optimization model so that I'll be able to say optimize certain criteria. Okay, based on what criteria I choose, maybe maximize benefits or minimize the deviation of targets and all those things. So maybe I could use based on criteria, I might develop the operating policy instead of this by some optimization. So this allocation policy could be based on say consultation among the group, or maybe based on some optimization model or development. What we are interested in is to understand how the reservoir is going to behave and try to analyze whether the behavior of the reservoir is as per your expectations. Okay, so you may know, say here, if I would like to stress about why the simulation I'm going for simulation here for this model, which could have been solved using optimization. So reservoir operation is done by say maybe develop an operating policy using optimization technique. People have been using vertical algorithm, maybe stochastic programming, vertical algorithm, various other kind of like particles optimization. So many methods have been evolved over the last few decades for developing the optimal operating policy of the reservoir. And similarly, there are models available for optimization and allocation policy. The question is, most of this, because of consultancy, you are trying to optimize certain criteria, but all the criteria that you are interested, you're not able to put in the proper method. So because of limitation of method model, sometimes many times you have to limit your objectives or goals that you are defined. So the simulation after the developing the operating policy will help us in understanding how the system is going to behave, and then maybe go back, revisit the optimization model and try to fine tune the say policies that you have developed based on optimization. That's where the simulation could be used in conjunction with the say optimization technique in order to improve the policies. So it's actually a very elementary problem, in fact, because the mathematics required is very simple here. You have a counter for time. You start with time t equals 0. What you need to do is assume some initial storage of the reservoir. So that's the initial condition, initial state of the reservoir always has to assume. So maybe you assume some initial state of the reservoir, let's say it's not, and then say you are implementing time. So you may read what is the inflow coming. So you may have some file which has the inflows sequence of flows that are coming to the reservoir. So try to find out what is the inflow coming to the reservoir. And then based on the policy that you have defined, you find out how much water is released and how much water is allocated to different activities and what are the benefits that you're going to find out and how much water will release to the reservoir into the river downstream. And then the simple transition function is based on a simple pattern equation. They say the storage for next time step would be equal to storage at the beginning of this time step plus whatever inflow has come during this time step minus whatever water that you have released from this. In fact, I should actually add one more component here, the losses that take place, because from the reservoir, you have losses in the operation or seepage and all those things. I may add minus the losses. But since the hypothetical problem, which is taken up as a case study, so its losses are neglected, but in real life problems, the losses could be significant. So all this, now, okay, you again, so you go to next time step and repeat like this till the end of the water sequence that you have. You may be simulating over a number of time steps that you have. And then all this computation that you have done, you store that in a form, and then later you need to analyze them and try to find out what is the performance. So maybe there could be different criteria based on which you have to evolve some criteria based on which you try to evaluate the performance. Because finally, the purpose of simulation is to evaluate how does the system perform. So how will the system perform? Now, as far as reservoir is concerned, maybe you may define different criteria for performance. Some kind of indices. Like in the case of reservoir, I can define some indices which will help me to find out how well I'm able to meet the demands, or what is the seriousness with which I say of not meeting demands. So some things I can develop some kind of criteria to which I will be able to judge the performance of the performance system. So in the case of reservoir, usually, for example, we use this criteria like reliability. So what does reliability indicate? Say what is the probability that you are able to meet the demands? Okay, so if I say 75% reliability, it means that I'm able to meet the demand 75% of time. Means the probability that I'll be able to meet the demand in a given time step or a given time period is 0.75. So there's a chance that I'll not be able to meet the full demand, the probability of 0.25. And then maybe other important criteria is resilience. What's the resilience? The ability of a system to come back to normal. So if there's a failure, the failure here is in terms of not able to meet the demand. So how well the system is able to come back to the normal condition, it is able to again, it's coming able to say improve its performance. So say when a failure occurs, okay, how well the system is bouncing back in normal phase, or how defined the vulnerability. Maybe I can say how vulnerable it is. What is the say, for example, okay, there's a deficiency, you are not able to meet the demand. So by what extent you're not able to meet it? So how serious is that condition? So if, for example, if say, so I'll take a maybe for example 100 years. In 100 years, even if I'm not able to meet demand for okay, or I'll take for example 365 days. I'm talking about daily, for example, daily. If, for example, I'm not able to meet the demand, say even 100 days, if the deficiency is very, very small, negligible, then maybe I'm okay with even deficiency of 100 days. But if the deficiency that whenever there's a failure is going to be very large, then obviously it's more serious. So maybe I can define terms of difference value. So I just took a small, so from this, okay, that's how you interpret the results. And then what's that you do based on the performance? Is the performance satisfactory? Is it able to meet? Is it able meeting your requirements or goals? So if not, then what is new? How do you modify the design? How do you modify the process? This is what you can do by putting results into the solution. Okay. I just put a simple numerical example here. Say I'm just taking a typical irrigation reservoir, a small irrigation reservoir, which is having a capacity of 50 million cubic meters. And let's say demands are like this. From June to September, demand is 40 million cubic meters. October to January, the demand is 80 million cubic meters. And February to May is 60 million cubic meters. And the month is the time step that I have taken here. Okay. Now here I'm just showing assuming that I'm taking a one particular typical year. Okay, I'm not trying to simulate over large number of years. I would like to know how the policy that I have developed earlier is going to perform for maybe, for example, a year which was the worst year. Worst year in the sense that the year was a very critical year, that was very low. Or maybe I'll take a year which is an average year, normal year. Or maybe a year which was the best year in the sense that very high flows, very low high flows. So I just taken 1 year, and these are the flows. As you know, in India, we count the year, water year from June to May. So this is 61 MCM is the flow that taken is come in the month of June. 108 is the flow that come in the month of July, and so on. Okay. So it's a very simple process. I assume the initially reservoir is empty because a small irrigation reservoir, most irrigation reservoirs are expected to become empty at the end of summer. So by the time of beginning of the monsoon season, reservoir is supposed to start getting filled up. Okay. For example, if I consider that the initial reservoir is S1 to 0, okay, then now what is that I have to next for next step? For example, is what I have a simple operating policy. Now I'm trying to find out what is S1 plus Q. Say Q1 is given as 61. So S1 plus Q1 is 61. So it's obviously more than the demand for that time, 40. So obviously I release 40. So what release that I'm going to make is 40. Please note that this example, I'm just confining myself only to the operation part, not the allocation part. I'm not talking about allocation part. I just confined the problem to only a part of the problem that I defined earlier. So I'll say RT is equal to 40. So what is remaining? 21. So the 21 will be the 21. Obviously, I cannot release 40 because if I release say 40, then 21 is remaining, but the capacity reservoir is also 15. 15. So how much should I release now? So I have to keep 15, and then whatever is remaining, I have to release. So I have to release 46. So I'm able to meet the demand. This month, June month, I'm able to meet the demand. So now the reservoir capacity, say storage of reservoir S2 becomes equal to 50. Now the inflow next time period area 108, and then again repeat the same process like this. We can repeat all the 12 months and then see how you are able to. So maybe this could be done as a simple kind of exercise. Maybe leisure time you can just complete this problem and then see how it works. Okay. Now I got the results of this. So finally, what I did is I just tried to count how many times I've not able to do that. So reliability I got is 0.75. Means out of the 12 months, I'm able to meet the demand, full demand as prescribed, only 8 months. 4 months, 3 months I'm not able to meet demand. So out of say 12 months, I'm able to meet the demand for 9 months, but 3 months I'm not able to meet it. So that means my reliability is 0.7. But the resilience, which is like the ability of the system to come back to normalcy, is 0.5. And the vulnerability, that is what I did is wherever there is deficit, I called it deficit, I took the average deficit. So the average deficit is around 14.75 MCM whenever there is a deficit. When you're not able to meet the demand, the deficit is something in the range of 14.75. Okay. Now, if I look at this problem, so as irrigation, for example, I'm interested to know whether this is satisfactory or not. Maybe in terms of reliability, it's okay because most of the irrigation systems are usually designed for what you call a 75% dependent loop. You only give an assurance that 75% time will be able to meet irrigation demand. So 25% time you will not be able to meet it. So from the reliability point of view, maybe yes, it's fine. This result is fine for me. But maybe resilience is very poor. So I would like to improve the resilience. Okay. So this way I can think of going back to the operation policy and see where I can modify and improve the performance. Okay. Even if reliability is, for example, I want to have achieve 90% reliability. It's a water supply project. I want to have 90% reliability. Then how do I modify this? Can I improve it? So this is where I can go back and then go back to the operating policy and see where I can modify the operating. So this is how the simulation can be used as a design problem. So you are actually trying to find out what happens if this kind of flows occur. But based on that, you are trying to go back and see whether you can modify, you modify, and again to repeat the simulation and see whether you are able to reach your satisfactory performance. Sorry. Now, in this problem, in this particular problem that I have taken up here, I just did the simulation only for one particular. So it's I treat this like a kind of a deterministic simulation because I just took one particular typical year, and for that typical year, I have simulated this. It's something similar to like I'm saying one event here. Even I'm defining in terms of one year. In a year, this is a typical year. This is a kind of flow that occur in a typical year. So if this kind of flows occur in a typical year, how is the problem? How the system problem? But actually, I would like to understand how my system behaves on a long-term basis, on a long period of time. So this way, because say this inflows, you don't know the inflows are uncertain and they never follow the same sequence. You have different sequences, different possible sequences. So inflows are completely uncertain. So in such situations, we go for this test simulation, what we call as Monte Carlo simulation. So Monte Carlo simulation, what we try to here is, okay, this system, you try to take multiple time series. In this previous example, I've taken only one time series, that is only one event. But I'll try to generate based on some, say, knowing the characteristic of the inflows that are coming to the reservoir, and try to generate different possible sequences of flows into the reservoir, monthly flows into the reservoir. And then we'll simulate this reservoir for multiple series of flows with multiple sequences. Whatever multiple sequences will simulate reservoir, and then we'll get different kinds of power. So I can try to use some statistical analysis of this output that I'm getting. Say for one sequence, I got some reliability, some resilience, and then vulnerability. If I simulate this over number of such sequences, I'll get different reliability, different resilience, and all this. So I can do some statistical analysis of this and find out the probability distribution of that, and then all those things, and then analyze that, and then see whether on a long-term basis my system is behaving as per my expectations. So this kind of analysis is what we call as multi-column simulation. What you're trying to do here is you're trying to generate multiple possible sequences of the random inputs that you need to analyze. Okay. I'll start the Monte Carlo simulation with a very, very simple example. In fact, it's called actually Monte Carlo integration. You may find most of the optimization technique textbooks. This example is given there. A typical example of Monte Carlo simulation. Just make you appreciate what is this Monte Carlo simulation. Okay. Say I want to find the area of a circle of unit diameter. The circle of heterogeneity. This problem comes under a category of problems called Monte Carlo integrations. So you're trying to integrate again, okay, because finding area under the curve is like integration. So when you don't have a different integration, you use integral method. So one kind of case going for this Monte Carlo simulation for which you try to evaluate the value. So here I have a say circle of unit diameter. I want to find area. This is not necessary, but people have used this kind of simulation to find the value of pi, because what's the area of unit circle of unit diameter? Pi by 4. So 4 times the area will give us the pi value. So this one way of estimating the value of pi through this Monte Carlo simulation. Okay. So what is that we get? So I've tried to put this circle. I hope you are able to see this picture. So I just embedded the circle in the square of unit square. Is a size of unit, 1 unit. Okay, I just take it a square. So within the square, we are embedding this circle. It is a unit circle. This is a unit diameter circle, and this is 1 unit square. Now, I can say because the center is 0, 0. So what are the coordinates of this? This will be -1, -1, and this will be 1, 1. This will say this will be 1, -1, and this will be -1, 1, and this is 1, 1. So these are the coordinates. Now, if I generate 3 points within this square, say over this domain of the square domain, if say I'll count this point whether this point could be the inside circle or outside circle. So if I try to generate a large number of points, and then from that find how many points are falling within circle and how many points are falling outside circle, and that will give me an idea of the area of circle. So I can take the ratio of so you just generate random points xy in 2D plane with unit square as domain. The square is your domain, and you generate large number of random numbers, let's say, to represent a point. So point is represented by x and y. So x ranges between -1 to +1. Y also ranges between -1 to +1. So generate to generate a point, you generate 2 random numbers between -1 and 1, and then say like that you generate number of points. And then if your x square plus y square is less or equal to 1, that point is inside the circle or on the circle. Whereas if x square plus y square is more than 1, that means falling outside circle. So what you're doing is essentially you're generating by fixing this limits, you are generating points over the square. And then out of that, you are trying to count out how many of those points are falling within the circle. Now I can say the ratio of the number of points inside circle to total number of points generated is approximately equal to the area of circle. So if I generate 100 points and say, for example, I'll say some 80 points are falling inside circle and 10 points are falling outside, I may say 0.8 is the area of circle. So this is assuming that all points are equal likely, and so the probability of a point falling within the circle is proportional to the area of the circle. You are generating points over a square of one square, but your area of circle is say 5 by 4. That means something like 0.78 or 0.76, something that range will get 5 by 4. So you are assuming that as you generate the points, random points, the number of points which are falling inside circle is proportional to the area of circle. So that is the idea with which. So now, why I've just taken this example is a trivial example. Just it helps you to understand what you are trying to do. So what is that you require here? You need to generate random points. Okay, this way Monte Carlo simulation makes use of extensively what we call as to be frank, actually the accuracy of this method depends upon number of points you get. If I just generate 10 points and then the solution that I make it not accurate. As you increase the size of your number of points, you are more accurate or more closer to your so the approach system that you have, you can do this in simple Excel file itself and maybe generate numbers, and you can generate thousands of numbers and then thousands of points, and then you can get an accurate value of the say the area of circle. Okay. Oh, so the entire Monte Carlo simulation, why I just mentioned this, is depends on random number. So you are trying to imitate the uncertainty and percent, and you are trying to use the, say some kind of randomization. So entire Monte Carlo simulation depends upon process of randomization. And you know that most of your systems have a, in fact, key or a function for randomization. For example, your normal calculator, hand calculator, you find there is a button for generating a random. So really, Excel, you can generate a random number in Excel also. So this random generation is a part of inbuilt in most of the software or most of the programming languages that we use in our day-to-day. So I just give a very brief, say, maybe idea about the random number generation. Um, Obviously, when I say a random number is supposed to be completely random. But once you say generate, that means you are using some mathematical equation to generate them. So we cannot. How can you say they are random numbers? So they're obviously what we call as pseudo random. We cannot call them random numbers. They're actually pseudo random. One of the very commonly used method for there are different methods called combination methods, additive combination method, multiplicative, and so on. But more popular, most of this software they use what is known as combination method, which generates sequence of random digits and numbers given by some equation like this: xn plus 1 is equal to a to xn plus c modulo m, or where this subscript indicates x is the random number that you're generating. Uh, so n plus 1 n means there's a sequence, you're generating for a sequence. Modulo is a function to take reminder. Means when you divide this axn plus c by m, what is the reminder that you get is what we call what you are taking as xn. For example, I divide 16 by 10. 16 by 10, what's the reminder? 6. So when I go for 16 modulo 10, the answer is 6. Okay. So that's what you're doing. A and C and M are the parameters of this model. And the quality of the random numbers are generated depends upon this. A and M, C should be very small in compared to M. And M usually should be very large because otherwise there'll be a cycle and also a sequential dependence. Once you have the sequential dependence, then obviously they are not random. So you need to choose the values of M and A and C. So M is usually choosing a very, very large number. And so that there's no cycle. If you take, for example, you can just try with taking M is equal to 10, and then A is equal to 2, and then C equal to 5, and then try to do it. You just initiate some number, and then try, you can generate. But you find that after a few numbers, it starts cycling. So if you choose a large value of X, the cycle begins. So these values of X will be obviously because you're saying a reminder, the values will be 0 to M minus 1. So in order to make it, say, this thing, you divide by M, xn plus 1 by M. So this you will get values between 0 to 1. Okay, some people also add some number like plus 0.5 before dividing this so that there will be some this thing. So maybe you can slightly modify this formula. But what you get as U here are uniform distributed numbers. They are, I hope most of you are familiar with probability and statistics or talking about different types of probability distributions. So we're talking about uniform distribution between 0 to 1. So what U would be a number between 0 to 1, which is uniform. Each value is equal likely. That's why I said uniform distribution. Uniform distributed number between 0 to 1. I can always transform this to some other uniform distribution number. Say, for example, I want a number which is uniform distributed between A and B. Then I can always convert this x U to y. Y is equal to B minus A into U plus A. So this y ranges between A and B, and is uniform. But all types we are not interested only uniform distributed random numbers. We are interested in generating random numbers of some other distribution. Okay. For example, this is a distribution that I have, which is this FDP distribution, and I have some random number R. So I want to find out some, say, this say, for example, a distribution, some other distribution other than uniform distribution. I always go for what we call as invert transformation. I just get an example of exponential distribution. For example, in the case of exponential distribution, the cumulative distribution, f of x is equal to 1 minus e to the power minus alpha x, where alpha is the parameter of this exponential distribution. So if I take a uniform distributed random number R, I can find x by taking the inverse of f of x. So x is equal to log of 1 minus r by minus alpha. For example, if I take this example, r is minus 0.25269, and let's say alpha is the parameter of the exponential distribution 0.2, then I'll get x equal to 1.116. So x is a randomly generated number which is having exponential distribution. So like this, there are different methods for generating the numbers, random numbers of different distributions. Normal distribution and say gamma distribution and so on, so many distributions. So maybe say if you go into a textbooks of any operational textbook, I think we find some discussion about the different methods of random generation and how you can transform that into different distributions. Okay. So with this, what I'll do is now I'll show how this random number generation useful in simulating the behavior of a system, what you call as multiple. So I'll just take a very elementary example of, in fact, I've taken an example of inventory control, inventory system. Uh, okay, I'll just take a small, a small numerical problem. Like, I assume that in a construction site, there's demand for bricks, and the weekly demand of bricks is uniformly distributed in the range of 600 to 800. The number of bricks required in a given week could range between 600 to 800 uniformly. And let's say you are placing order whenever the quality of bricks in the inventory falls below 750. And let's say every time you order, say place an order for 1,000 bricks. Okay. And your cost of ordering is, let's say, 150, and then holding of bricks in the inventory is 0.5 per brick per week, which shortage of cost is 2. So those are familiar inventory systems that we gave. In fact, I can actually use some optimization models. There are methods for finding out what's optimal value of this, what you call as reordering point, and what's optimal value for this quantity of that you're going to order. But let's say, based on some, say, some analysis, I got these values, the 750 and 1,000. Now I'd like to know, how is my system going to behave? Okay, the inventory system is going to behave, and then maybe you want to analyze it. Again, I don't want to go into deeper analysis here because I can do a lot of analysis. I can try to find out, for example, I'm interested in finding out what's the probability of shortage. Or maybe I'm interested in finding out what's the average cost of maintaining the inventory, or what's the typical cost of maintaining, or what is the shortage and cost of shortage. So like this, I can try to identify different criteria on which I'll try to evaluate this inventory. But I'll just make it very simple. I just talk in terms of inventory. Now, this I can do in a simple Excel. I just try to do this in Excel worksheet. Okay. Again, just like in the result operation, I just need to assume some initial stock. I assume that initially I have 1,000 bricks in my this thing, and then I generated a demand over 14 weeks using the same process that I used earlier. So to generate random number in Excel, you can generate random number from 0 to 1, and that random number from 0 to 1 I can convert it to random number between 600 to 1800, because that's the range of this. And then decision about when to order, and then what's remaining, and based on that, say when if I do this analysis, so I'm just looking at only 2 points here. How many times the shortage is? Okay, I find that out of 14 weeks, 7 times there was shortage. Is I'm not able to meet the demand. What I mean by shortage here is I'm not able to meet demand. So please note I'm not talking about how much was the reduction and all those things. Also, I can do analyze. I'm just taking only that part of my this thing from that Excel sheet where I've solved to just explain only the part of. So I'm just only interested in the possibility of a shortage, the probability of a shortage. And what I find here is the probability of shortage is 0.5. Again, please note that this 0.5 may not be a correct value, it might be accurate value because I just simulated over 14 weeks. If I simulate a larger time period, for example, simulate over 1,000 weeks, maybe I would have got slightly different answer. So maybe I cannot base my answer on a small number of simulations, but for a classroom like this, I obviously I cannot go for it. So I just try to do it for only 2. So what I find is the probability of shortage is 0.5. So maybe my focus is on, say, probability of shortage. How can I reduce the probability of this shortage? Okay, because I find this very high. There's 50% chance that I'm not able to meet the demand on the customer side. Obviously, that will cause delays in my construction activity and all those things. So I would like to improve. So maybe, for example, let's say I'll go back to revisit this problem and let's say I said number of bricks ordered. Whenever I place an order, I'm placing order for 1,000 bricks. So why not change it? And when I place an order, I'll say, let's say I'll order for 1,500 bricks. Okay, so if I order 1,500 bricks, then what happened is number of weeks which shortage actually is 4, and the probability has come down to 0.2. Okay, this just what I'm trying to here is I just took two alternative decisions. One is place or say when I'm placing order, I've not changed that. That policy is same. Whenever say the size of your stock becomes 150, I'm placing order. But if your stock, if how much I am placing order, if I say 1,000 and 1,500, I make comparison. Obviously, I find this better for me in terms of the probability of shortage. I'm not looking at the economics point of view of all those things. I'm just looking at one point. So this why so this is now this will help us to actually say this how I can try to revise my policies and then see which policies. But please note when I have large number of alternatives, simulating for so many alternatives becomes very tedious. And reason why you need to have an optimization model, but most of the time the optimization model will only work on average condition because now you have uncertainty like this. You are trying to only optimize the expected conditions. But how it behaves under extreme conditions, what you can understand from by the kind of simulation. And based on that, you can go back to your optimization model and maybe do some kind of fine tuning and try to improve upon your solution that you obtained. Okay. Just last, I'll just show another simple example. Okay. This is like, for example, I'm trying to simulate this, say, construction activity. I just borrowed this picture graph from by Hillary Level Manufacturing Operation Research. For example, you have different activities like excavation, foundation, rough wall, roof, and so on. These are different activities, and this is the flow chart. And maybe, especially those who are with the civil engineering background, you have studied PERT and CPL, and you know how to find out the say critical path and then all those things. These numbers that I given here, they are the number of weeks to complete that activity. For example, to complete the activity A, it takes 2 weeks. Then to complete this 4 weeks. Then to complete this 10 weeks, C activity. So like this, if I take the critical path and based on this, what I can find is I can complete all these activities in 44 weeks. Problem that the construction faces is these durations are expected values. Mostly these are expected values. And there is a lot of uncertainty in the duration. That's the reason why most of the time in building activities, you plan, say you assume, you expect that you complete your entire construction activity in 6 months, but it may take 8 months, 10 months, 1 year, and so on. So there could be a lot of delays because of various reasons which are not written. So all these numbers that are given, they are not mistake, they are not considered. So obviously, if see, for example, this is a project and I as a contractor, I want to know whether I bid this or not. And let's say there's a delay, say the client is going to impose a penalty on this. So I'd like to know what could be the time that I can subscribe for a result to complete this activity. So I'd like to analyze. So this kind of follows. Obviously, say if this are all assumed uncertain, maybe based on the past experience that I have with the similar kind of construction activities, I can find out that on average it will take 2 weeks. But maybe I can find out what's the distribution. For example, I'll say it's normally distributed with B equal to 2 and standard deviation equal to 1 week or 0.5 week. Let's say 2 weeks with a standard deviation of 0.5 weeks. And this may take 4 weeks on average and is normally distributed with a say standard deviation of let's say 0.25 weeks. So like this, I can, based on the past analysis of data, past experience, I try to understand what's the probability distribution of all these activities. Now I can perform a simulation, what I call a simulation, where I write down, say, the activities and from the start to finish, different paths, and then generate random numbers to generate the duration of these different activities. This here I have to generate random numbers of normal distribution with the given parameters. And generate random numbers and then like that create different scenarios. And then based on all these scenarios, analysis of these scenarios, I can try to find out what will be the time of completion of this thing and what could be the probability of delays and how many weeks delays could be and all this analysis I can make and then maybe use that in my analysis to really understand say before I bid for this. Okay, so this is just an example where another example where this multiple simulation. So maybe I can go on giving a lot of examples, but maybe I would like to just wind up with a small summary here so that we can spend some time on discussion because I find some questions also coming up. So maybe we can these things. So other one, when talking about simulation is a very widely used modeling system for complex, used for modeling complex systems. There are a lot of advantages of simulation, but mainly the advantage here is that compared to automation techniques, the simulation model does not have any kind of, there's not bound by any kind of a typical mathematical structure. And you need, say, your objectives or your, say, criteria for evaluation, the performance, all these things could be not be also very, say, defined very precisely. With all these things, maybe simulation is still useful. But the problem with the simulation is it's time-consuming process because when you have large number of functions. This is why most of the time we try to combine optimization simulation techniques. I just gave an example which I borrowed from a book by Bujendar on water systems modeling techniques analysis. For example, you are trying to say water quality management. You are looking at water quality management river. So maybe you need a physical process to simulate the physical process to understand the pollution transport. So you are generating a lot of say waste and then disposing waste into the river. So you have different options of treating the waste. So what you're trying to decide is how much waste has to be. So maybe you need to decide some, maybe you can try to use some simulation process to decide what will cost the range of values of this decision variables. And then based on that, now develop an objective function of minimizing cost of treatment, all those things, for different combination of decision variables, and then get some solution. And then using that solution again, go back and then simulate your entire process. And then find, maybe you can change the decision variables or range of decision variable and change the objective functions or model, and then again run the model. So like this, still you converge. So this how maybe like the same thing can be applied in inventory control or like in the reservoir operation problem. You develop an say operating policy based on optimization technique. Simulate, use simulation to evaluate the performance. So, for example, when I develop an operating policy, maybe reliability, resilience, all these things cannot be directly incorporated into my optimization model. So that could be a limitation. So maybe I'll evaluate the performance later, and then find out if I am not satisfied, then I'll go back to optimization model, then try to modify it based on my experience with the simulation, and then run again. So like this, you can run it and you can combine the so that's how the simulation in conjunction with say observation techniques is very useful, especially when you're dealing with complex systems where there's a lot of uncertainty. That's why I say complex stochastic systems. With this, I come to the end of my talk. So we have, I think, around 15 minutes time for question and answers.
Thank you very much, sir, for your nice explanation on this simulation. The question in chat box is how to decide minimum reliability requirement.
Yeah, well, I saw the question actually. This is actually okay. What is the reliability requirement is obviously system dependent. Now, depending upon your your requirements. For example, I was saying when I talk about a water system, as a water system, water source person, I can talk about water system. When I'm designing a water system, usually a convention is that a irrigation system usually is designed for 75% rating or dependent. Reason is, in the case of irrigation projects, maybe you have some, say the requirements are huge, you need large amount of water, and there could be some alternate source of water also, like groundwater and the rainfall and all those things. So maybe you may say that, okay, even if you are able to meet a certain level of dependability, there's some deficiency, there could be reduction in the yield, but still it's fine. Whereas when you talk about domestic water supply, for example, you are talking about domestic water supply to a city, obviously you cannot go for 75%. At 25% time, you cannot say that, okay, we're not able to supply demand. So you try to find out your source because there'll be no alternate sources and be difficult. So there, obviously, you give a higher level. So reliability depends on both your system requirements and also on the economical considerations. So maybe providing a very high reliability sometimes could be economically profit-free. So you would like to restrict the reliability based on the economics.
I think one more question is there, how to simulate boundary conditions?
I saw the type. completely didn't understand what you mean by boundary conditions. Also get the boundary conditions. Maybe if that participant can unmute and then ask, it will be easy for me to understand the question.
Please unmute Madhuri Ganorkar, madam. Madam, raise your hand so that you can be.
I see one more question that's come in the beginning of my lecture. That is wind energy forecast system belong to stochastic? Okay, anyway, it doesn't come under this purview, but definitely wind energy forecasting system obviously is stochastic. Because wind itself is stochastic, wind is uncertain, and obviously, we're talking about forecasting the wind energy, it's obviously a stochastic system.
Okay, I think I don't find any other questions.
Okay, I think that Madhuri, maybe she is not able to speak.
Yeah.
Yeah, okay. Boundary conditions, I don't know what we mean by boundary conditions here. No, but see, when you boundary conditions, obviously boundary conditions are say governed by certain equations, a set of equations. You may, for example, you are talking about a say I'll just take an example of flow in a say river, for example. Now, at the boundary, obviously, there are certain conditions to that are governed, and then you have a certain equation governing the boundary conditions. So you have to run those mathematical equations to simulate the behavior. That's all boundary condition. It's what at least to whatever I understood from your question. That's what I can answer.
Yes, sir. Yeah. Any other questions in question and answer? No, no questions in question and answer. Okay, thank you very much, sir, for your nice explanation about this simulation. And it is always it is our pleasure to be with you and to see you offline as well as online, both. Previously offline, now since 1.5 years we are meeting online. So thank you very much for support to this ATAL FDP. And participants definitely they might have benefited about this basics of simulation. So thank you very much, sir.
Thank you all, and thank you for this opportunity. And hope this lecture is useful for most of you who are especially those who are into modeling techniques and using models for your research. Thank you.
Yeah.
Thank you for giving this opportunity to Dr. Bilwa.
Yes, sir. Thank you very much, sir.
Okay. Bye, and wish you all the best for all the participants, and hope this FDP is successful for the next 2 days also coming, and you'll have a successful and fruitful deliberations over this week till this weekend. Thank you.
Yes, sir. Thank you very much. The next session, it will start by exactly 3:30. Now that session is not like technical, but it will help you for your life skill management and stress management. So Himanshu is a faculty in Art of Living. So he will conduct the session. So the contents and all overall contents, I know that it is regarding some life skill management or stress management, but definitely he will touch each and every aspect of life skill management. That is what I hope he will take it. So this session, that is a stress management or life skill management, it is a mandatory session from AICTE, ATAL. So it is a part of scheme document that we have to conduct one session. So that is what, as per schedule, it is from 3:30 to 5:30. So being he is from the spiritual organization and all, he will be in time. So 5 minutes, 10 minutes before only he will join. And I request all the participants to be in time and enjoy that session for 2 hours. Okay, thank you.